So if I'm going to find the equation of a tangent line or the equation of any line at all, what are the two things that I always need to be able to write the equation of a line? I have to have a totally need a slope. And what's the other thing I'm always going to need? I have to have some sort of point. Now, sometimes that point is the y-intercept, but more generically, I just need a slope and a point. So our calculus, like go-to version for the equation of a tangent line is y minus y1 equals m times x minus x1. Now I know y equals mx plus b, totally fine also. This one lets us put in a slope and a point. So it's usually the better starting point for calculus, even if we're going to have to rearrange to make it say y equals mx plus b. So I'm going to start with the point. I didn't give us a point, I give us half of a point. If x equals 1, I need to know the y value also in order to turn that into a point. So I know my y value is going to come from plugging in 1 to my equation, and I've got e to the, it's going to look like 1 squared minus 1. Try to keep our numbers easy so we wouldn't have to reach for a calculator yet this morning. 1 squared is 1. And 1 minus 1 is 0. So this is really e to the 0, which is 1. You shouldn't have to reach for a calculator. If that is not a fact that's readily available in your head, add it to your list of stuff that you want to memorize, because this is one of the nicest values we can be given in terms of e to something. So I've got my point, so I can go ahead and plug that in. I'm looking at y minus 1 is equal to my slope times x minus 1. Since I'm looking for the slope of the tangent line, I know that's asking me to take the derivative. So now comes the calculus-y part. If f of x is equal to e to the x squared minus x, then when I go to take the derivative, I'm going to need to use a little bit of chain rule. So the derivative of e to the something is e to the something times whatever the derivative of that something was. So I'm looking at e to the x squared minus x times, and this is that chain rule part, the derivative of x squared minus x. And what's my derivative of x squared minus x? So I'm going to have 2x from that x squared part. And then the minus x is going to turn into a minus 1 when I'm taking that derivative. And I only care about the slope at a very specific value of x. I only care about the slope when x is equal to 1. So I'm going to get my actual slope by looking at f prime of 1. We already know that when we plug in 1 here, 1 squared minus 1 gave us 0. So I'd have e to the 0. 2 times 1, that'll be 2, and minus 1. What do you know? I gave us really nice numbers for the whole problem. That's looking like 1 times 1. So my slope is just 1. So my equation here, y minus 1 equals 1 times x minus 1. If you want that to look like y equals mx plus b, totally can. I could add 1 to both sides and distribute my slope through. And turns out my equation of the tangent line simplifies really nicely, and it's just y equals x. So the first thing that I would do, because I always want partial credit, and if I run out of time working the problem, I at least want someone to know, I know what it looks like to have a tangent line and to plug in a point. So I'm going to go ahead and get my y minus y1 equals m times x minus x1. And I'm going to go ahead and plug in that point. So I would have y minus 0 is equal to m times x minus pi over 2. If I want a little bit more partial credit, even if I mess up the derivative, I at least want to show someone that I know what I should be doing. So I know that I'm going to get that slope by taking the derivative and plugging in pi over 2. That really is worth some partial credit. And so I at least want to get that far in case I get stuck on the derivatives or I just run out of time. Now I can start the calculus part. So the first thing that I want to notice is if I've got x cubed times cosine of 3x here, I'm going to need a product rule. So I've got an f and a g. So when I go to write that derivative, I like to give myself parentheses because I know I'm going to have 4 things that I have to pull together for the product rule. And in those parentheses, I've got to put all of the pieces. So I'm going to need an f prime times g and an f times g prime. I'm going to go ahead and put the pieces that I don't have to take derivatives of yet. So I'm just going to stick in my cosine of 3x and I'm going to stick in my x cubed. Now I'm going to sprinkle on the calculus. When I take the derivative of x cubed, I'll have 3x squared. And when I take the derivative of cosine of 3x, good morning. When I take the derivative of, oh, there's a great question in the chat. I'm going to loop back around to that in a second. So when I take the derivative of cosine of 3x, I'm going to need to use chain rule even for that. But I'm going to look at that cosine and say derivative of cosine is negative sine. And I mentioned this before, but I really want to drive this point home. Calculus cannot change the argument of a trig function. Only trig identities can. So whatever is inside of your trig function can't change from you taking a derivative, meaning this is going to be sine of 3x. The chain rule part that I have to put onto that is to multiply by the derivative of the inside. And the derivative of 3x is going to be 3. Okay, so there's a question in the chat about how do you know when to use the product rule? I would say whenever I have 2 functions specifically, not talking about a constant. Whenever I have 2 functions multiplied together, I should be thinking about product rule. Now, one of the real subtleties to this problem, and I'm going to read our overall function one more time. This says x cubed times cosine of 3x. And the reason that I'm reading that as an of is it's easy for our brains to see those parentheses and think that this is cosine times 3x. But a trig function always needs an angle. It always has to have an argument. So that means that the cosine 3x, that whole thing is a function. I can't separate the cosine from the 3x. So this cosine of 3x piece, now that I'm looking at like the cosine of 3x times the x cubed, that's what's telling me that I have a product rule. And then the thing that's telling me that I have to use this chain rule is that this is anything other than just an x inside. Although technically, if it's just an x, you could write the chain rule also, but the derivative of x is 1. So this is cosine as kind of like an outside function with 3x on the inside. And that's the whole idea behind chain rule. If I have a function like captured inside of another function, that's when I have to use the chain rule and multiply by kind of the derivative of the inside part. Should we turn that into a slope? There's a lot going on visually, so I'm going to rewrite this, just kind of cleaning it up a little bit. So for my derivative, I got 3x squared cosine of 3x. I'm going to take that minus sign and that 3 and stick them out in front. So minus 3x cubed sine 3x. So I want to, there's a question in the chat and I will certainly loop back around to this. That 3x is not multiplied by cosine. This is not a product rule. What it is a chain rule. So this 3x is inside of the cosine. So our derivative ends up looking like the derivative of the outside function times the derivative of the inside function. And that's what the chain rule is. Hopefully that answered the question in the chat. We'll find out. Okay. So when I go to turn this into my actual slope, I know I've got to plug in pi over 2. And I've given us pretty nice numbers, but this is going to look a little bit gross. How do you square pi over 2? You just write pi over 2 squared. It's fine. And that's going to be cosine of 3 pi over 2 minus 3 times pi over 2 cubed times sine of 3 pi over 2. Now cosine of 3 pi over 2, it's either 0 or 1. Which is it? Good guess. It's 0. Yeah. So if you are a unit circle person, totally a place that you could use unit circle. If you prefer to think about the graphs of sine and cosine, that's fine too. But unless you're being allowed to use a calculator on your quizzes or midterms, you will need to have the nice trig angles memorized. So if you've somehow been avoiding it up to this point in your life, the time has come. You are a flashcard person. That's a great place for flashcards. Quizlet, if you'd rather have your flashcards digitally, there are tons of Quizlets out there for trig facts. You know, you're sitting on the bus, you're waiting in the line at the dining hall or the coho for some food, be practicing that trig stuff. So cosine of 3 pi over 2 is 0, which is going to mean this whole front piece goes to 0 and I don't have to worry about. Sine of 3 pi over 2 is -1. So I've got -3 times pi over 2 cubed times -1. We could choose to simplify that a little bit. It's not going to simplify a lot. -3 times -1 will at least make that positive. I could cube the 2. So I could have a positive 2 pi cubed over 8. And I think that's probably as simplified as we can get. So for my final answer, I just need to take that slope and stick it in right there. So I am looking at, I think I can squeeze it in here, y minus 0. So I could actually leave the 0 off if I wanted to, times that slope, 3 pi cubed over 8 times x minus pi over 2. And that's going to be my equation. So I want to get our derivative going together, and then we can decide if y'all want to try the algebra part on your own. But so using that power rule, the way the power rule works, I take the coefficient, I take the exponent, I multiply it by the coefficient in front. So here there's like an invisible 1. So I'd have 5 times 1. And then we subtract 1 from the exponent. So I'd have 5x to the 4th minus 4 times 3 is going to give me 12. And then I subtract 1 from the exponent, so I'll be at 3. And here, I know it looked gross because I gave us a fraction, but luckily when I multiply by 3, the 3's are going to cancel out. So I'm going to be left with 7x squared. if I'm setting that whole thing equal to 0, personally, I'm hoping that something is going to factor. And right away, I can pull that x squared out. So that I've got x squared and then 5x squared minus 12x plus 7 is equal to 0. There are lots of different techniques for factoring. And I know the numbers are kind of big and gross. But if it's quadratic, you always have the option to do quadratic formula. And if you're really terrible at factoring, I recommend practicing. But if you really, really want to fight the factoring, you can use quadratic formula. In this case, our numbers are kind of big. So quadratic formula isn't going to be super wonderful, but we could fight through it that way. Would y'all like to see a technique for factoring where you're like, I got this? What? Okay, so one option for factoring, sometimes we think about this as like the Xbox method. If you have something that works for you for factoring, just keep doing it. Okay, but here's one option for us. And people put things in different places. So I'm gonna make my bottom be the B value. If you put it on the top, that's okay too. And I'm gonna make my top the A times C value. So I would have 5 times 7, and I would put a 35 right here. And I would put a -12 down here. And then I'm looking for two numbers that add up to -12 that multiply to be 35. Conveniently, 5 and 7 multiply to be 35. And if I make them both negative, they're going to add up to that -12 I was looking for. So one option for how to go from there to what factors is to kind of do our multiplication box, but in reverse. This is not our only option. So I know that I've got to end up with that 5x squared and that 7. But I'm also going to need a -5x and a -7x. So that those two terms would add together to give me the -12. And then from each row and column of the box, I factor out whatever they have in common. So on the top, I could pull out a 5x. And on the bottom, I could either think about this as pulling out a +7x or a -7x. I'm going to go ahead and pull out, a +7 or a -7. I'm going to pull out a -7. Try that and see what happens. So now I need to put something up here so that 5x times that gives me the 5x squared back. So it's going to have to be an x. And x times -7 would give me the -7x in that box. 5x times -1 would give me that -5x. And -1 times -7 would give me that 7. So I now have my factors. 5x minus 7 times x minus 1 is going to give me 0. Happy to show y'all another way to factor. I would say this is a little bit time consuming, and this is probably the way that I would have taken the time to factor like in a pre-calc class, or maybe once upon a time if you took algebra 2 or math 3. Lots of different labels on things. I find at this point, the fastest thing is really to just take that 5x squared minus 12x plus 7. And if I were factoring this and I needed to do it pretty quickly, I would really just look at the first and last terms. There's only one way to get a 7. I have to have a 7 times a 1. I might have to mess around with positives and negatives, but the only way to get that 7 is with a 7 and a 1. The only way to get a 5x squared is with a 5x and a 1x. So I really only have 2 options. I either put the 5x here or I put it here. And then I would kind of multiply those out in my head. So it turns out that if I tried putting an x here and a 5x here, then I would end up with the 5x squared I wanted and the 7x that I wanted, but I would have a 1x plus a 35x. And that would not give me the negative 12. So I would know this direction didn't work. I would have to put in the 5x and the 1x. And then I just have to mess with the plus or minus signs to get me to the negative 12. And that's where I would need both of these to be negative in order to have the negative 7x and the negative 5x. Again, none of that is calculus stuff. So if you have other techniques that are working for you to factor, you can use any technique you like, as long as it's working. So all of that was just to get us to this lovely thing being factored so that I can pull off the x values where the slope of my tangent line is 0. Well, the value of x that makes x squared 0 is x being 0. And the value of x that makes x minus 1 0 is if x is equal to 1. And this one, it's okay if you don't want to do it in your head. You can take the steps to write out 5x minus 7. If I set that equal to 0, 5x is equal to 7 and x is equal to 7/5. So those are my 3 x values where the slope of the tangent line would be equal to 0. Haven't seen any questions coming through in the chat for a minute, so I'm just going to pause.
Okay,
Yeah.
It's just like capturing because they're not contributing.
So if you're finding the derivative using the limit definition of the derivative, in order to evaluate that limit, you might have to do different algebra techniques. Here, we've moved on from that limit definition of the derivative, and now we're starting to use sort of shortcut rules for how to do the derivatives. And so here, the derivative is actually done at that step. That was the only part of this problem that was taking a derivative, and that was using the power rule. Everything after that is the algebra stuff that we need in order to answer the question. Calculus is like 90% algebra, 10% calculus. Like in terms of what you're actually doing. So if you think about all the limit problems, really it's mostly algebra. When we're doing applications of derivatives, it's really mostly algebra. When we're simplifying derivative answers, it's really mostly algebra. So the calculus is mostly algebra. More practice? Oh, yeah, what did I say? We needed the points. Cool. So if I'm going to find the points, then I really need to plug each of those back into the original function to come up with the y values. So, cool. So f of 0, that one's pretty easy. 0 to the 5th times 3 times 0 to the 4th plus 7/3 of 0 cubed. I get 0. So 0, 0 is one of our points. F of 1, also not too bad. 1 to the 5th minus 3 times 1 to the 4th plus 7/3 of 1 cubed. So that's 1 minus 3 plus 7/3. And if I wanted to combine that, I'm going to need a common denominator, but first I'll do the 1 minus 3 and get -2. So I'd have -2 plus 7/3 and get a common denominator by multiplying that one by 3/3. 7/3 minus 6/3. So I'm at a positive 1/3. So that point would be 1, 1/3. And I'll be honest, that last one is going to be particularly gross. And I'm going to show y'all what I would do if this were a quiz or a test and I needed to write that as a point and I was short on time. I would write that final point as 7/5, comma, f of 7/5. Now, I'm not wrong. That is a correct answer. So I'm not going to lose points for having a wrong answer. Might I lose points for not simplifying and making that a number? Possibly. But if I'm short on time, I would rather leave a correct answer that's not simplified than possibly make a mistake rushing my simplification. Oh, how do I know that this is a chain rule problem? I have a function sitting inside of another function. I'm going to have to do chain rule. Why do I know it's not a product rule problem? Trig means nothing without an argument. These 3 letters, T-A-N, might be something that happens if you go to the beach, but it's not a math thing until there's something with it. So tangent of x, now it's a function. Tangent of the square root of gross, now it's a function. But just tan is a thing that doesn't really happen to me at the beach, but other people. So the first thing that I'm going to do if I know it's a chain rule problem is I might want to rewrite this because I need to have layers to peel off for chain rule. So that 3 right there is actually telling me, so I'm not taking a derivative yet, that 3 right there is telling me that I have a whole thing raised to the 3rd power. And the thing that I have to the 3rd power is tangent of some gross stuff. Now, the other thing that I want to be able to do is to use that power rule. I don't want to think about that as a square root. I really need to think about that as some stuff to the 1/2 power. Now I'm ready to take the derivative using chain rule. One of the things that's easy to happen with chain rule is to kind of get lost of what you've taken the derivative of already. So this is where I love having 2 different colors. And I'm going to use one color to kind of mark off the parts that I've taken the derivative of. So my most outside function here is that I've got some stuff to the 3rd power. So just using our power rule, I know that's going to look like 3 times that stuff squared. And I'm going to mark off that I took the derivative of the power rule part with that 3. And I've just got to rewrite the whole thing. So tangent of 3x to the 4th minus 2x whole thing to the 1/2. So now if I've peeled off that layer, the next thing that I'm going to hit is tangent of some stuff. And the derivative of tangent of some stuff is secant squared of the same stuff. Again, calculus cannot change the argument of a trig function. Only trig identities can. So when you take derivatives of trig stuff, whatever is inside stays the same. So 3x to the 4th minus 2x whole thing to the 1/2. And again, I'm going to mark off. It took the derivative of the tangent part. Next up, I've got some stuff to the 1/2 power. So I'm going to use that power rule, bring that 1/2 down, and then subtract 1 from the exponent. And 1/2 minus 1 is going to give me a negative 1/2. Took the derivative of the 1/2 part. And then I'm not going to change what's on the inside. Now I'm ready to take the derivative of what's all the way on the inside of the function here. And that's that 3x to the 4th minus 2x. That's the last thing I'm going to take the derivative of. Derivative of 3x to the 4th, I'll bring that 4 down. 4 times 3 is 12. Subtract 1 from the exponent, so I'll have 12x cubed. Derivative of negative 2x is just going to be negative 2. And I'm done. So if I take a step back and look at the overall structure of this problem, it's definitely a quotient rule. I've got a giant division sign there. Now, sometimes when we look at when I've got a giant division sign, if the bottom is just a single monomial, then sometimes I can avoid quotient rule by breaking it up into separate fractions. But this denominator, there's not a whole lot I can do with it. So we're definitely going to need the quotient rule here. Do you all want to practice this one on your own, or did you need to watch me do another one? Okay, I got some watch me do another one. Totally fine. The first thing that I'm going to do with this problem, and I would do this even if it were just that numerator or just that denominator, my first step would still be to write all of the radicals that are happening in the problem as fraction exponents. Because if I can have a number times some stuff raised to a power, it's always going to be a friendlier derivative for us. So I'm not going to take a derivative yet. I'm just going to write this so that my numerator is x to the 1/2 plus x to the negative 3rd. And my denominator is going to be x squared minus 3x whole thing to the 1/3 power. So in terms of a quotient rule, kind of like the product rule, I'm going to go ahead and give myself tons of space on the paper, but I'm going to have the derivative of the top times the bottom minus the top times the derivative of the bottom. And I'm giving myself, I hope, lots of room. And then the bottom squared. Great question. Can I distribute the 1/3 power? Sadly, no. If I've got stuff in parentheses and I've got addition or subtraction in there, the radicals don't simplify. So this is not equivalent to saying the cube root of x squared minus the cube root of 3x. All of that stuff inside the radical is like glued together by addition or subtraction. So it's stuck in there. There's nothing I can do to simplify. Okay, in terms of my quotient rule, I know this has to look like derivative of the top times the bottom, leave the top alone, derivative of the bottom, bottom squared. I'm going to go ahead and plug in the parts that don't need the calculus yet. So the bottom, I'm going to have x squared minus 3x to the 1/2. On top, I had x to the 1/2 plus x to the negative 3. And on the bottom, x squared minus 3x whole thing to the 1/3 power. I don't know why I wrote a 1/2, 1/3. There we go. That's all the not calculus part. Now I'm going to sprinkle on the calculus. So when I go to take the derivative of the top, I've got a power rule thing happening. Derivative of x to the 1/2 looks like 1/2 x to the negative 1/2. Derivative of x to the -3, I'm gonna squeeze just a little more space for myself. I'm gonna bring down that -3. And then being careful, -3 minus 1 is -4. So my new exponent there is a -4. When I take the derivative of the bottom, I'm going to need the chain rule. Or I can think about this also, the book calls it the general power rule, because I've got like power rule stuff inside the parentheses raised to another power. So my outside function is that I've got stuff to the 1/3 power, leaving me with 1/3 times stuff to the -2/3 times the chain rule part says I've got to multiply by the derivative of what's on the inside. Derivative of x squared is going to be 2x. Derivative of -3x is -3. Walk away. Do not try to simplify this.